In this second example, we are also trying to find the natural frequencies of a beam in transverse loading, but unlike example 1, we have a fixed pinned beam instead of a fixed free beam like we had before. We can recycle a lot of the work that we did in example problem 1, but we're going to have slightly different boundary conditions, and those different boundary conditions are going to affect the natural frequencies. Everything else, though, about the beam is the same material, the same radius, length, all of that is the same. So kind of recapping what we did on example problem 1, because this too has a constant material and a constant cross-section, we can use that simplified PDE that is the equation of motion of this beam. We have free vibrations as well. Based on the PDE, we know that this is a separable function. So W of xt is going to be this W of x, the eigenfunction, times t of t. And using this W of x and the boundary conditions are how we're going to find the natural frequencies of the system. So the boundary conditions, very similar to problem 1, as I said before. If we look at x equals 0, well, it's still fixed to the wall there. So it's the same first two boundary conditions. We have W of 0 is going to be 0, so the position or the deflection at the wall is going to always be 0 at all times. And the slope at the wall, W prime of 0, is also always going to be 0. Our third boundary condition from example problem 1 also applies here. The internal bending moment is still going to be 0. So we're pinned at x equals L, and a pin can hold a force, a vertical force or a horizontal force, but it cannot hold a moment. So it will still be true that W double prime at L is 0. But now what's different is at the free end, or we don't have a free end, we have a pinned end, we cannot say that the internal normal force or the internal shear force is 0 at x equals L. But because we have a pin connection there, we can say that the displacement, the vertical displacement, has to be 0 at all times. So different than the previous version of this example, our fourth boundary condition is actually also on the position, that the position at L is going to be 0. First three are the same as example 1. Fourth is now different. W of L is 0. In the previous one, W triple prime of L was 0. So how does that affect our boundary condition equations? First three are exactly the same, so I just copied them through. So our new one is now W at L is 0. So if I use that W of x equation and now I apply specifically W of L, I will get C1 cosine beta L plus C2 sine beta L plus C3 cosh beta L plus C4 sinh beta L. So from this, I want to make this A matrix, which actually the first three rows are going to be exactly the same when I pull out the C1, the C2, C3, C4, because the first three boundary conditions have not changed. So it will still be 0, 1, 0, 1, 0, then 0, 1, 0, 1. And the third one, I will get this negative cosine beta L. I will have a minus sine beta L, a cosh beta L, and sinh beta L. And now the fourth row is different. I have a cosine beta L positive, a sine beta L positive, cosh beta L positive, and a positive sinh beta L. So different A matrix, and now I'm multiplying it by that C vector is equal to 0 because they're all homogeneous boundary conditions. So again, I have this A matrix times C equals 0. So what I need to enforce so that C is not also the 0 vector is that the determinant of A must be 0. And like the first example, I want to find all of the beta values that make this true. The betas are then going to translate into my omega n's, and that's how I'm going to find the natural frequencies. So I have a different A matrix than I had in the first example. I want to find out what is its determinant. So once again, I'm going to use Mathematica to do this step. So same process as before, but with these different boundary conditions, I can assemble this A matrix, or once again AB, as I'm going to call it in Mathematica, and I am going to set its determinant equal to 0. And actually, I'm going to do some further simplifications by hand than even Mathematica is doing. So when I take its determinant and set it equal to 0, this is that scalar equation that I get. And I could put this right into MATLAB and find the betas that make this true. However, I want to simplify it a little bit to give MATLAB a little bit easier of a time to try to find the betas that are going to set the left-hand side equal to 0. So I'll transcribe directly that determinant out of Mathematica that I will then be able to modify a little bit. So cosh beta L sine beta L plus 2 cosine beta L sinh beta L. And that must be 0. All right, so I have these 2's I can cross out right away. That's going to make this a little bit easier. And I can also reduce the number of trig terms or trig and hyperbolic terms that I have as well. So for example, again, the right-hand side is 0 here. I have a cosh times a sine. I have a cosine times a sinh. So what I'm going to do is divide both sides, left and right, by a cosine term. So I'm going to divide this by cosine beta L and this by cosine beta L. And also the 0 has to be divided by cosine beta L, but cosine beta L is always non-zero. L is not 0, and B is going to be something that is going to be non-zero as well. So the cosine of beta L is going to be a non-zero value. And I can also divide by a cosh beta L. Again, everything will get divided by the cosh beta L. Right, so I'm allowed to do this. I'm doing the same thing to both sides of my equation. These coshes are going to cancel, and these cosines are going to cancel. And the right-hand side is going to remain 0. So why did I do all of this? Because now my first term is sine beta L over cosine beta L, which we can also call tan beta L, so the tangent of beta L, plus sinh beta L over cosh beta L is going to be tang, or hyperbolic tangent, beta L equals 0. So this is a little bit more compact a way to find the betas. I now have only 2 functions, a tan and a tang, that I need to use in MATLAB, rather than a cosh times a sine, a cosine times a sinh. MATLAB would be able to do it in the original way it came out, but the simpler we can give it in MATLAB, the better chance it has, and the faster it's going to be able to find all of those solutions for beta. And before looking at the MATLAB, I'll point out I forgot to bring down that negative sign, so it's a negative tangent beta L plus tang beta L. That's going to be the function we're trying to find the roots of. Looking at the MATLAB, I established some of the parameters right away. Our length is 2, as it was in example 1, and setting up some of these initializations for when we go into the loops to find all of the beta values that are the roots of this equation. So let's first just plot our function, this tangent minus tang. I did here reverse the signs. It doesn't make a difference because the right-hand side is 0. But here we see these 4 points on the plot that are of interest, but these are not zero crossings. These are actually asymptotes. So by visualization, we can't clearly see where these 0 crossings are, and that's why we want to use this systematic way of finding these zeros. It's not obvious from looking at the plot. So we're going to use the same method we used in example 1, where I'm going to start using f0 with a guess that is just a little bit bigger than 0, and try to creep up on the smallest beta value, the first beta value that satisfies this equation, so the first root. So I'll run up to this while loop and see what the first beta value is. Right, so the while loop has finished, and we are getting a Q, which is the first beta value of 1.96. So let me save that into my list here. Right, so once again, what did I do? I went to this while loop, and I keep increasing my starting guess a little bit at a time until I have found a positive beta that satisfies that tangent beta L minus tang beta L equation. So first one, 1.96. Then, like before, I'm going into this for loop where I'm going to now try to find the next larger one, the next larger beta value, by guessing a little bit bigger than the previous beta value, and then continue that process as I go. So once again, to avoid duplicates, I'm looking for every beta value to be at least 10% different than the previous one. So I'll run up to that point and see what the 4 beta values are. Right, so it's finished running, and I can look at my beta list. So these are the first 4 betas. I'm again assuming I haven't missed any, and I'm trying to ensure that by making sure that this starting guess only gets a little bit bigger every time I run it, and also here that I'm saying it's a 10% difference, assuming it's not going to be any smaller than that, that a true root is going to be at least 10% bigger than the previous root. Again, possibly that's wrong. I could miss a beta this way, so playing with this value, making it smaller to a certain degree, could help just verify that I've not skipped over one of the roots of this, but by making this too small a value, I'm going to be picking up duplicate values of beta. But regardless, these are the 4 beta values I get, and I can translate those into then the first 4 natural frequencies for the system by squaring each one, multiplying it by c, as we did previously. So if we run this whole thing, get our beta values, then we get here the first 4 natural frequencies are about 1950 through 22,500. And I'll put in with more detail what those are. Now keep in mind that everything about the beam is the same as it was in the first example, except it's a pin connection at the right side rather than a free end like it was in example number 1. And that did indeed change the natural frequencies. And we can take a quick look and compare the natural frequencies we're getting for the fixed pin versus what we got for the fixed free. Coming back, I'll transcribe those first 4 natural frequencies. The lowest was 1950 radians per second, 6,300 radians per second, 13,200, and 22,500. So taking a quick look here, 1950 is our lowest with the pin, 22,500 is going to be our largest. Bringing up the previous example, our lowest natural frequency when we had the free end was lower, 494, and also the 4th natural frequency was lower than we're finding here with the pin. It was only 15,256. So by adding that pin at the end, instead of keeping it free, raised the natural frequencies, at least the first 4 that we observed, in this system. So putting in a more constrained right side increased the natural frequencies for the same beam, everything else about the beam being the same.